Welcome to another session of the supervised machine learning section, and today we are going to talk about decision trees. So under supervised learning we talked about classification, and so decision trees is another way of classifying things. So first, before going into decision trees, let's look at some kind of a data point distribution. So let's say we have some points, say like these orange points here, like this, and then let's get another set of points here. So we have these purple points over here. We have the purple, and over here we have the orange. So what's special about this data set is that it's linearly separable. So you can see that I can separate these two classes with a line. So what happens if this is not linearly separable? Let's say I have something like let's say I have something like this. So I'll take the same colors. So bear with me while I draw this. So you can see that we can't draw a line around this kind of a distribution. So you can see that if we are to separate this, we'll need something like this. So this is not linearly separable. So when we encounter a data set like this, that's when decision trees comes into our rescue, right? So let's go ahead and try to do a simple decision tree on this dataset. So let me get this into a new page. All right. So now let's assume that these are our x and y coordinates, right? Here we have x and here we have y, and here in a decision tree what we are going to do is we are going to try to draw different lines and use a multiple stepped approach to separate our data, right? So first let's draw our first line in red, let's say. So we draw our line like this. Let's say this is this line is y equals 5, so we say so we can say that y greater than or equal to 5 separates this into two sections. Okay, I might need to resize this, so bear with me. So let's say that y greater than or equal to 5. This separates our data set into, let's see, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So on one side we have 14 purples, and on the other side we have, okay, it's fun to count this, 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 24. So we have 24 purples and 1 2 3 4 5 6 7 8 9 10 11 and 11 oranges. So it seems like we need to find a couple of more lines before we can actually separate this data. So let's choose the same color. Let's choose red for our line. So we are gonna draw another line, let's say through here. So let's say this is x equals 2. So that means after we are looking at we look at the line y greater than or equal to 5. So on this side this is true, this is false, right? So here on the right hand side we do another conditional division, so that would be x greater than or equal to 2. So here we have the true side and here we have the false side. False side would be this side, right? So out of these 24 purples and 11 oranges, we have 1 2 3 4 5 6 7 8. We have 8 purples on the false side. On the true side we have now 16 purples and 11 oranges. Looks like we need another line, so let me draw another line. So let's say this is, I don't know, y equals 3. So from this node here we can draw the next line. So we say y less than or equal to 3. On the true side we have 1 2 3 4 5 6 7. We have 7 purples, and on the false side we have, what's left should be 9 purples and 11 oranges. So I'm running out of space again. Let me resize this. So all right, now we are looking at our right hand side, or the false section. Again we need to separate this data, so let me separate it. Oops, let me separate it once again. I'm calling this x equals 4. So I'm gonna have a node here, x greater than or equal to 4. So now you can see that on the true side we have our 9 purples, and on the false side we have our 11 oranges. So now we have approached what we call leaf nodes. So I'll circle our leaf nodes in green. So leaf nodes are any node where we have data points of only a particular class, right? So when we look at some of these nodes, we have just one color, and some nodes we need to go further down the track to properly classify our nodes. So this is basically a decision tree. So you might be wondering why this approach is actually a machine learning approach. So I found it quite easy while looking at the dataset, but choosing where to draw these lines, that's where the machine learning is, right? So before we go into that, I must say that sometimes it's not possible to completely achieve all leaf nodes, but what we would do is sometimes we may have, let's say if we had a rogue orange dot here, what we are going to do is we'll have an orange dot here, right? So sometimes what we do is we will do a vote here. So let's say like we have a new node coming in, we have a new node here. So what we do is we go through this tree, and when we go through this, y greater than or equal to 5, false. So I'm just gonna trace it here, false, and then we say x greater than or equal to 2, false. So that means our new node is going to be a purple node. Let's say we have a new node coming up on this section. Now you see like it is not necessarily a leaf node anymore because we have an orange dot. So but when we come all the way here, we see that it's not a leaf node, but so it is a leaf node, but it is not a pure leaf node. So what we are going to do is we'll take a vote. Okay, so 9 data points say that it should be a purple, and 1 data point say that it should be an orange. So we say, okay, it's more likely that this new data point here is a purple data point. So that's how decision trees work. So let me quickly erase these new nodes, and let me erase this one as well. All right, so we have our decision tree and our data set. So as I mentioned, the hard part is actually figuring out how to draw these lines. So how do we do that? So this is where we need to look at this concept called information theory. So let's look at information theory then. So in information theory, we look at the entropy of something. So let's say we have our original data set. So we have this entire data set, and we see that there's there's like massive number of purples, and then 11 orange dots. So if we look at the entire picture without our red line, so let me just copy this so that we can have a look at it. Okay. So we are basically looking at this and trying to decide how much information is there. Like, so if let's say if it was entirely purple, then we pick something and we are entirely sure that anything we pick would be purple. So that means it has a very low entropy. But let's say if it is like 50-50 orange and purple, then there's like a lot of uncertainty. It's as uncertain as it could be. So we call that a high entropy, or the highest entropy, which is 1. So in this case we had, if I remember correctly, we had 11 oranges and 14 plus 24, 38 purples, right? So how do we calculate entropy? Is the sum of probabilities for each class. So pi times log of pi. So this logarithm could either be like log of 2, or it could be a natural logarithm, or it could be the log of base 10. So depending on what kind of log you choose, entropy is calculated in different units. So I'll just give an overview of that, right? So you don't really need to know this. So the standard unit of measurement is in log 2. This is called a Shannon. So entropy used in log of base 2 is called Shannon's, while this is called nats and this is called dits. So because my calculator on my computer can only calculate either nats or dits, I'm going to use nats because it's more natural. It's because it's a natural logarithm, but doesn't really matter, right? Anyway, so here we have the equation for entropy. So let's calculate the entropy of our initial state. So that is the probability of ith class times the probability of the ith class taken as a logarithm. So and then so we have two classes, so let's write it this down. So minus probability of orange is 11 out of 49 times log of 11 out of 49 minus 38 out of 49 times log 38 out of 49. So this is the entropy in nats for this initial scenario. So let me calculate that. So let me calculate this. I think I may need a more advanced calculator for this. It's just my simple calculator in the computer wasn't keeping track of what I was typing. So I'm going to use Wolfram Alpha. Unfortunately, I can't share that with you, but what I'm doing is the same calculation on the screen. And so I'm doing this at this moment. Alright, so I calculated the first part and that turns out to be something like 0.33 and minus 38 that is 0.19. So let's take this to be 0.20. So yeah, so sorry, this is actually plus because this entire part is negative. So we get the number 0.197 something. So I rounded up to 0.20. So the total entropy of this situation is 0.53, right? Okay, so that took some time, but so this is the uncertainty in this particular dataset. let's see what happened when we drew that first line. So I'm talking about this line, the line y greater or equal to 5. So let's just write it here, y greater than or equal to 5. That meant, just a moment again, bear with me. So yeah, so that meant 14 on one side and then 24 and 11 on the other side. So let's calculate the entropies for these two children. Right, so we have child 1 here and child 2 here. So you can do this with me as well. So entropy of child 1 is quite easy. This is sum of p0 times log of p0, and this is like minus, I forgot the minus sign. So this is 1 times log of 1, which is 0. So this is a 0 entropy state. And then we have the entropy of C2. So this is the probability, this is minus, well, here there's two classes, so 24 out of 35 times log 24 out of 35 minus 11 out of 35 log 11 out of 35. So alright, let me calculate this. I'm just gonna calculate it directly. 24 over 35 times log 24 over 35 minus 11 over 35 times log of 11 over 35. So this is giving us 0.62 as our entropy. All right. So now we have two children whose entropy values we know as given here, right? And now what we are going to do is we are trying to look at what our information gain is, because in information theory, information gain is important as well as entropy. So information gain is defined as, let's see, information gain is the entropy of the parent minus the sum of entropies of the children but weighted. So entropy of each child, right? So let's calculate the entropy gain from our parent into here. So our parent's entropy was 0.53 minus, and then we have the sum of the weight, and then we need to take the weight. So basically here we had 14 children, and on the other side we had 24 and 11, so 35 children. So altogether we had 49 children. So 49 or sorry, what was this? 14. So 14 over 49 times the entropy, which is 0. Don't need the summation here, so plus 35 over 49 times 62. So I hope you can calculate this with me. 0.53 minus just 0, and then this is 35 over 49 times 0.62. This is 0.62. So we have our information again as 0.087. So we have gained some information, but it is not the best. It's like it's barely it's barely better than the parent, right? So the entropy is barely less, but we have gained information. So this is how we go on to select where to draw the line. The machine learning algorithms would test many lines. They would be like, okay, should we draw the line here? Should we draw the line here? So they'll draw many lines and try to select the one with the best information gain. So that is a decision tree for you. In the next lecture, we'll be talking about random forest, which is a collection of decision trees, which is like used quite often in machine learning. So I think this lecture is dragging on for a little bit. So I'll stop here, and thank you for joining me. I'll see you with random forests in the next lecture.